What if adding one cache server invalidated almost every single piece of data in your cluster? That's exactly what happens with naive modulo hashing. Consistent hashing fixes it, and it's why your favorite databases and CDNs can scale without mass reshuffling. Let's start with the broken way. A cluster of 4 nodes, and you pick a server by hashing the key and taking modulo 4. If you add a 5th node, nearly all keys will remap because the denominator changed. For 10 nodes going to 11, about 90% of keys move. That's a disaster. Cache invalidation, database thundering herds, unnecessary data shipping. The problem is that the mapping function depends on the total number of nodes. Consistent hashing decouples key placement from the node count. Imagine a large hash ring, 0 to 2 to the 32 minus 1. You hash each server's identifier, maybe its IP, and drop it onto the ring. Now a key arrives. You hash the key onto the same ring and then walk clockwise until you hit a server. That's the owner. When you add a new server, it only claims keys that would have been served by its immediate clockwise neighbor. No other servers are affected. On average, only 1 over n of the keys move, where n is the number of nodes. Remove a server, and only its keys shift to the next node. But wait, if you just place a handful of physical nodes randomly on the ring, you'll get hotspots. Some servers end up owning huge arcs, while others own tiny ones. The fix is virtual nodes. Each physical server gets hundreds of virtual replicas scattered across the ring. You typically use 100 to 200 virtual nodes per physical instance. Now, the arc ownership becomes statistically even. Adding a physical node still moves only about 1 over n of the keys, and the load distribution stays smooth. Cassandra uses this technique, and it's why you can add a node and see a well-balanced rebuild. Let's look at how you'd build one. The core data structure is a sorted list of hashes with their owning node. When you add a server, you compute a hash for each of its virtual nodes, maybe by hashing the server ID plus a replica index, and insert them into the sorted list. To find the node for a key, you hash the key, use binary search to find the first virtual node with a hash greater or equal, and wrap around if needed. The same approach works in any language. The ring becomes a simple ordered collection with O of log k lookups, where k is the number of virtual nodes. In production, when you add a node, you don't have to stop the world. You insert its virtual nodes into the ring and immediately start routing writes to the new owner for those keys. Stale reads can be avoided with a read repair or hinted handoff strategy. Because the movement is small, the added load of data streaming is predictable. If you double your cluster size over time, the total reshuffling cost grows slowly, not explode like modulo would. Consistent hashing solves the reshuffling problem, but it doesn't solve uneven access patterns. If a few keys become extremely popular, they'll still land on a single server and create a hot partition. Virtual nodes can't help with that because each key is deterministic. You have to split those hotkeys at the application level or add some smart request routing. Another edge case is when you add multiple nodes at once. They might cluster together on the ring and steal from the same neighbor, causing a temporary imbalance. So you either add them gradually or use a placement strategy that spreads them. So when should you reach for it? If your cluster size changes frequently, autoscaling, rolling restarts, adding capacity on the fly, you need it. If you have anything beyond a few nodes, the bounded key movement saves you outages. When should you avoid it? If you run a small, static 3-node database and you almost never add or remove servers, the extra ring maintenance isn't worth it. Also, if you require perfect equal distribution of data by size, range partitioning with manual splitting might be more precise, though you lose the smooth rebalancing. Picture a production cache cluster with 10 servers storing session tokens. If you add an 11th server using naive hashing, 9 out of 10 entries get remapped, turning into cache misses that smash your database. With consistent hashing, only about 1/11 of the keys relocate to the newcomer. The database barely notices. The difference between a manageable scale-up and a full outage often comes down to this one choice. Let's recap. Consistent hashing maps both nodes and keys to a large hash ring, and a key always finds its clockwise successor. Adding or removing a node only affects the immediate neighborhood, moving about 1 over n of the keys. Virtual nodes make the distribution even, typically 100 to 200 replicas per physical server. This mechanism is running inside Cassandra, DynamoDB, CDN routing, and modern service meshes. It's the reason dynamic clusters can grow without burning the whole data plane. When you need to rebalance with minimal pain, consistent hashing is the pattern you want. Thanks for watching. I hope this one was useful. See you in the next video.